All right, now I'm going to do F1-20. I know these are getting a little trivial, but I figured I would just do this one because it has a stepped shaft where you have this intermediary loading, so at least this makes the free body diagrams a little more interesting. Here we go. This is going to be another one with a factor of safety. Again, we have a factor of safety 1.5 against yielding. It gives you the yield stress of the material as 50 ksi. If you don't know about factor safety and yield stress, look at what I solved, problem 119. I discuss it there. And what it's looking to find is design H1 and H2 as small as possible for each one of those to the nearest eighth inch. So it allows these things to be sort of shaft material that goes in eighth inch increments for yielding. Okay. Oh, okay. It's a rectangular bar. I'm sorry. It's a rectangular bar. So through the thickness of the page is a half of an inch. Okay. So but they want H1 and H2. All right. So it's a rectangular cross section. All right. So each element has a rectangular cross section. This is a half of an inch, and this is the height. H1 here. I'm sorry. H2 here and H1 there. All right. Okay. F1-20. All right. So, well, let's just get the max stress allowable. So the maximum stress, normal stress that's allowed is going to be the yield over the factor of safety, right? And in this case, that's going to be 50 ksi. That's 50,000. Oh, I'm sorry. I could have zoomed out. It's tough with the videos. No one can tell me when I'm doing something wrong. All right, there we go. Now you can see. Okay, F1-20. We're going to figure out the maximum allowable stress. This is the stress that's going to be in our design. It's the yield over the factor of safety. The yield, theoretical yield, is 50 ksi. That's 1,000 pounds per square inch. And the factor of safety is 1.5. So that gives me a maximum allowable stress for the design of 33.3 ksi. All right. So now let's go forward and let's figure out the design. All right. So the first thing to do is we have two areas we have to worry about. We have to do an analysis on the H1 cross section between B and A, and then the H2 cross section between C and B. So we need free body diagrams of both of those. All right. So let's first do H1. So if we look at H1, we're going to do a cross section. Right? We're going to do analysis through this cross section here. Right? This is going to be between B and A. So we get something that looks like this. We have applied here. Oh, it's in compression. I'm sorry, I have the wrong way. It's going this way into compression of 30 kip. And then, like always, I always put the normal internal reaction normal such that it's positive in tension, but you can choose, it's a force, so you can choose whichever way you want to. That's a bit of confusion here. All right? And now when I do the free body diagrams on this, we can see that N is equal to minus 30 kip. Or it's in compression, okay? 30,000 pounds. In compression. That's the compressional force. So it's actually acting in the other direction. All right, so this gives me the stress, the average normal stress is N over the cross-sectional area at 1. In this case, this is going to be the 0.5 inches times H1. N is in kips, all right? You can see the sign. This is the reason I like to do the internal reaction force is always positive in the sense such that you get the correct stress convention. So here the negative is going to make this a negative stress. and now that's a compressional stress. You can do it the other way, but you just have to do the bookkeeping in your head and remember that's a compressional stress. In this problem, it doesn't matter because we're going to assume that the yield is, sort of the same in compression or tension, or that they've specified this such that you know it's in compression, it works out. In general, well, not in general, some materials do have different responses in compression and tension, like concrete. And you have to be careful, but in this situation, they kind of set it up for you. All right, so I know this is going to have to be the sigma max. This is the max allowable. All right, so now I can solve for H1. So the sigma max equals n over 2n, bringing the 1/2 above there, H1. And so solving for H1, I get H1 is equal to 2n over sigma max. So that's 2. Let's go all into fundamental units to make it easier. So this is 1,000 pounds. So it's 2 times 1,000 times 30. That's pounds over the sigma max, which is 33.3. It's in pounds per square inch, so I put 1,000 up here, and then that gives me pounds per inch squared. There was an inch unit here from the 1/2, right? So that's going to knock out one of these. These guys cancel out. The thousands cancel out. And that gives me inches. So that gives me 2 times 30 over 33.3 inches. So it should be about 2 inches. 60, enter, 33.3 divide. So it's 1.80 inches. And now the problem asks you to get that to the nearest eighth. All right? So 1 3/4 is 1.75. 1 7/8 is 875, I think, right? 7, 8 to 5, right? 1.875. That is 1 7/8. 1.75 is 1 6/8, or 1 3/4 of an inch. Okay? So which one should it be? Obviously, you should err on the over design, so that means H1 should be 1 7/8. Okay? It's a little bit over the 1.875, so you have a little bigger than a 1.5 factor safety. You can actually figure that out if you want. All right, now we do the second part. We'll do the same analysis at a cut between C and B. All right? So again, at the end, we have the 30 kip force here, and then we have these two shoulder forces, each of 15 kips. All right. I mean, in this one, you know, let me just mention something. Some of you might be tempted to look at the shear along this line, okay? And you could use the cross-sectional area. The problem is they don't give you the length. You would have to know this length to determine the shear across this area. Also, they haven't really given you the yield shear stress. It's kind of the reason why I don't like some of these problems. Kind of set you up. If you left it a little more abstract, you could go through that thought process. But it's a bit of a cop-out, but in this case, we're going to ignore shear because the problem hasn't been set up to do the shear, all right? If they gave you the length, and then they also gave you the yield shear stress, you could do a shear analysis on this one. But you know, the way they kind of drew it, that looks like a bigger area. The shear yield stresses are usually a little less than the normal, but it looks like it's been more than compensated up by the length, assuming, you know, it's to scale. So again, you could check that, but in this case, probably you can infer that it's not what they want you to do. All right. So here we get the normal force, the internal reaction normal. In the second section, N2, and again, I've drawn that such that a positive sense would give me tension. Obviously, it's going to be negative. You can do sum of forces, and you can see that the total, it has to balance minus 2 times 15 kip minus the 30 kip, which is just going to be a negative 60 kip. All right? So that's that reaction force. So it's going to be a compressional reaction force of 60,000 pounds. All right. We can go through the same analysis. In this case, sigma max. We're going to let that be the design stress is going to be the one divided by the yield divided by the factor of safety. That's equal to the average normal stress, which is N2 over the cross-sectional area. This area again is going to be 0.5 inches times H2. So now we can solve for H2. H2 is equal to 2 times N2 over, I got an inch down here, and then sigma max. Okay? And so that gives me 2 times minus 60 ki kips, right? Over, not to get confused with the kips with the KSI, over, I got an inch down here. Sigma max is the 33.3 KSI. The K's kind of cancel out. I got an inch squared, inch. The units work the same way as before. And so now I get basically H should be double what it was before. I mean, so this is 60 enter 2 times 33.3 divide. So I get here 3.60 inches. All right. Well, I guess I should break this out. I dropped the sign in here, but this is the same as we talked about in class on Thursday. Obviously, you know, I should really talk about this being the sigma max and this being the absolute value, right? Because really, we're assuming it's failure and compression and tension is sort of to the same degree. Okay. All right, so there's that. Now we got to round off to the highest eighth of an inch. So 3.5 is 3.5, and then if we go to 3 and 5/8, that is 3.625 inches, which is the next eighth increment above this. So H2 should be 3 5/8 inches. Okay.